This lecture starts out at the very beginning of this pre-calculus/math analysis textbook with lines in the plane and discussing slope. Seeing this in the greater context as a preview for calculus, slope of a line is directly or indirectly related to the entire branch of differential calculus and derivatives. And so a lot of this will be a review, but occasionally there'll be a little bit more depth to what you would have seen compared to times past. So first of all, slope of a line is how fast it's changing vertically compared to its horizontal change. It's a simple enough formula, y2 minus y1 over x2 minus x1. Of course, you can switch those as long as you do it on the top and the bottom and you're consistent about that. And we're talking about lines here as being straight lines. Equations for finding slopes of lines. This is just basic Algebra 1 stuff. You did this Algebra 1, Algebra 2, geometry as well, plugging into the formula. It's good, though, to check your work as far as understanding that this should have a slope of 0 because it's flat. This is a positive slope. Here's a negative slope. And here we have a vertical line, so it's undefined. This is a bit of a summary of what I was just saying. So positive slope rises from left to right. Negative slope falls. We have 0 slope, and we have our undefined slope. Can't divide by 0. Point slope is not an equation form you might have used as often as, say, slope-intercept, but it's very useful, very valuable. Here it is, y minus y1 is equal to m times x minus x1. Another way to view point slope form is in the context of transformations. If you think of the line y is equal to x, and then you transform it by multiplying by m, which is like your a value, or your b it could be as well. And then this minus x1 would be your h value. If we add y1 to the right, we would have plus y1, which is like your k value. So in terms of the a, b, h, and k, you can think of point slope form perhaps as transformations of the basic function y is equal to x. So here we have a point, here we have a slope. We simply plug into this form of the line. This is correct, this is correct, this is now slope-intercept form. Useful, of course, to put it in your calculator. Looking way ahead when you get into things like AP tests, either one of these is fine as well. Here we have a linear model for something. So $12.25 billion in 2004, 2005, $13.74 billion. We're assuming a linear function, so we want to predict net sales for 2006. So we need a couple points for our to get our slope. So our first one, we'll let times 0 be 2,000. So we get our first point is 4 for 2004, comma 12.25 because it's in billions, and then 5, comma 13.74. From now we find our slope. Then we take our slope in either one of the 2 points, plug it into point slope form, and then if you want to get in slope intercept, you can distribute and add, and you get down to here. Then in order to find out the net sales in 2006, you plug in 6 for x, and you can get the predicted net sales. Throughout the beginning of this text, you see these library of parent functions. It's a good idea to have this a nice basic idea of what certain functions look like so that you understand their domains, the ranges, and that way it's easier to know what applications they have and what sort of transformations you can do with them. And so here we just have our basic linear functions with intercepts and domains and ranges and whatnot. Okay, graphs of lines. Basically, you need 2 points to graph a line. You can always use more to check, but you don't need more than that. You can use it do it using intercepts, using slope, just plugging numbers in. There's a variety of ways to go about it. I don't think we need to spend more time on that. This is more types of equations of lines. This is sort of a general form. You often see this as ax plus by is equal to c, where we put the c on the other side. Here's our vertical line, x equals a constant, where this constant would be the x-intercept, or horizontal, y equals a constant, where this constant is the y-intercept, slope-intercept, of course, and point slope. The different viewing windows is very important. Going over to this note for a moment, we see that this is the line y equals x, given these window settings. Negative 10 to 10 for x, x scale 1, y scale negative 10 to 10, y scale 1. This is the line y equals 2x, and we have our same x min, x max, but our y min, y max are negative 20 to 20, and our y scale is 2. Now visually, when you look at them, these are exactly the same pictures, but it's important to realize that due to the window, you can get very different outcomes. And so this is one way of showing that window is important. Another way would be to graph a function and then stretch it around and shrink it using windows and focusing on different parts, and you can make some functions look a lot flatter than you would expect them to be, or steeper and whatnot. But it's important to note what the window is for your display, because that can affect the way you interpret your graph. Parallel lines, of course, have the same slope. So if you want to find slope-intercept form through this point parallel to this line, you need to find the slope of this line, so get it in slope-intercept form. And then our slope, of course, is 2/3, so we use the 2/3 slope and this point in order to put it in point-slope form. So that would be down here, and then we can simplify it further if need be. Perpendicular lines have slopes that are negative reciprocals, or if one's horizontal, the other one's vertical, would be the other possibility. And so we have this line. It has a slope of 2/3, so the negative reciprocal is -3/2. We use the slope -3/2, the point 2, -1, put it in point-slope form, and then simplify to slope-intercept form. Here's a couple perpendicular lines. Notice again the window makes a big difference. We go -10 to 10, -10 to 10. They don't necessarily look perpendicular, but if we make our window more square, so to speak, and noting that the horizontal length of the actual picture is bigger than the vertical length, so we account for that, now it looks more perpendicular. So you can't always trust the graphing calculator. One more example of point-slope form. Here we have a couple points. We want to get in this form. So we find the slope by doing y2 minus y1 over x2 minus x1. We get a slope of -2. You can use this slope and this point to get this equation, or this slope and the second point to this equation. These would be the exact same equation. It would be clear if you were to distribute the -2's and simplify. You would see they'd have the same slope-intercept form.